Alright, this is example 9.2.8, the gamma pivot, and my name is Will Hastings. I'm working with Cameron, Jose, and Kelly. And suppose that we are given some xi through xn, which is an identically independently distributed set of random variables with following an exponential distribution with mean lambda. Then what we can say is that f of x1 through xn with parameter lambda is equal to the product from I equals 1 to n of 1 over lambda e to the negative x over lambda, or our population PDF. Then, doing some arithmetic here, we can pull out n copies of 1 over lambda, and then we can go ahead and take this product and put it up into the exponent and switch it to a summation. As such, after factoring out this negative 1 over lambda from each of our random variables within the sample. From here, we notice that this portion right here does not rely on lambda, and we can call this our sufficient statistic t, which is equal to, t of x, which is equal to the summation of all of our x random variables. Then t is going to follow a gamma distribution with parameters n comma lambda, which has the PDF of gamma n lambda to the n, all of that raised to the negative 1, t to the n minus 1, e to the negative t over lambda, where this is actually going to be a scale family. And this is important because we can set our pivot quantity q of t and lambda equal to 2t over lambda by multiplying by a scale factor of 2 over lambda. Now, this is actually going to allow us to set our pivot quantity q of t lambda to a gamma distribution n comma lambda, where we then multiply that lambda by our scale factor 2 over lambda. Notice that our two lambdas cancel, and so this is now this is now equal to a gamma distribution in comma 2. And let's take a look at that PDF. When we look at this PDF, what we notice is that it is very similar to a chi-square distribution. In fact, if we set n equal to 2p, if we set n equal to p over 2 for our chi-square distribution, then what we can do is solve both sides for p and find that p is equal to 2n. And so this way we find that our gamma distribution, or gamma of n of 2, is going to follow a chi-square distribution with 2n degrees of freedom. We're going to pause in the explicit example just for a moment, because in example 9.2.8, the gamma pivot, it breaks midway through and then begins discussing the general form of the concepts. And then we'll take these and then we're going to turn it back towards that explicit example momentarily. I also want to make a note that I am working with Jose, Cameron, and Kelly. Okay, so in general, the PDF of a statistic t can actually be written as such. F of t given the parameter theta is equal to some function g times our pivot quantity q of t and theta times the absolute value of the partial derivative of our pivot quantity. And I actually just want to make a note here. So just for example, to relate it back to the example earlier, we set our qt of theta equal to, I believe it was 2t over lambda. And just simply note, if we were to derive this with respect to t, then what we would get is 2 over lambda. And this was our scale factor that we multiplied through our gamma distribution. Okay, so just kind of relating that to the example earlier. Okay, so now that we have picked our pivot, how can we construct our confidence set? So we want to choose a probability with respect to theta for some a and b for a specified alpha that don't actually, the A and B don't depend on our population parameter theta, okay? And then we're going to set our pivot quantity in between those two values of A and B. Then what we'll do is for the null theta, the null population mean, which is an element of our parameter space, we're going to set this to A, the acceptance region of theta naught, is equal to x given A is less than or equal to our pivot quantity less than or equal to B. And then from here, we can use a test inversion method that we learned in a different chapter to obtain our C of x, our confidence interval of our null population mean, such that A is less than or equal to our pivot quantity less than or equal to B. And from here, we can use this 1 minus alpha confidence test where we can actually set it up in the following way. We can create our confidence set such that we have a lower bound of x comma A is less than or equal to theta less than or equal to u of x comma B if we know that our pivot quantity is increasing, or we have another set, the lower bound of x comma B is less than or equal to theta less than or equal to the upper bound of x comma A, where notice our A and our B are switched whenever our quantity x comma the population mean, our pivot quantity is decreasing. Now that we've set up these kind of definitions for constructing our confidence set, let's go ahead and return back to the explicit portion of our example. Okay, so here we have our gamma pivot, part 3. And let's just take these things back from our explicit example from part 1. We know that we have IID x1 through xn, which is following an exponential population mean lambda, and we've defined our test as the summation of all of our xi's, all of our random variables, and we have our pivot quantity t lambda, which is 2t over lambda, and we also showed that this was following a chi-square distribution with 2n degrees of freedom. Now there's one thing that I needed to mention in part 1 that I did not. So when we got our gamma distribution n comma 2 earlier, the one thing that I needed to note was that this this distribution does not rely on lambda, and that is in fact why we can choose it as our pivot quantity. So with that being said, let's go ahead and say this. We'll set the probability with respect to lambda that we can choose some A less than or equal to our chi-square distribution with 2n degrees of freedom less than or equal to B, such that this is actually greater than or equal to 1 minus alpha, where we can replace this chi-square distribution with 2n degrees of freedom with our pivot quantity test comma lambda, and then we can make a further substitution where we can take our probability with respect to lambda from A less than or equal to, and we'll replace our pivot quantity with 2t over lambda. Now let's go ahead and do some arithmetic here to get to our inversion method. We now want to solve for lambda, so let's go ahead and multiply all three pieces here by 1 over 2t times 1 over 2t and times 1 over 2t. I want to add that we were doing this work inside our acceptance region of lambda, and here we have our acceptance region of lambda, or for lambda, for t, such that we have a over 2t is less than or equal to 1 over lambda, less than or equal to b over t. Now this is where we're going to use our inversion test method, and so in our next thing what we're going to have is, once we invert this, we get our confidence set for lambda such that 2t over b is less than or equal to lambda, is less than or equal to 2t over a, and since 2t over lambda is decreasing as lambda is increasing, this is why we saw that our b and our a switched. And this concludes our gamma pivot example.